Yes, let's start. Okay, moment. So this lecture, we will continue speaking about algorithmic probability and Solomonoff induction. I mean, just optimizing algorithmic probability. And we will just derive some properties. For example, we will compare it with Bayesian induction for a simple experiment where we drop a biased cone. So binomial variable, we drop a cone a few times and we want to know what is probability of heads. And there is a known result that says that any estimator for this probability, the variance will decrease to 0, but the sum of the variances will diverge. But for Solomonoff prior, so if the bias is rational number, the estimate will converge. So this will be a consequence of a theorem by Solomonoff that says that in fact, so Solomonoff induction can approximate any, so it defines conditional probability, and that converges very quickly to any computable conditional measure, provided the sequence is generated from this measure. So basic, in simple words, it can model anything that's somehow computable. Which is very strong result. And so therefore, people could view this algorithmic probability as like a magical prior distribution for Bayesian reasoning. So this is one interpretation. But okay, let's repeat what is definition. So let's repeat a little bit from previous lecture because it was not too coherent from my side. So I guess it doesn't harm. So by the way, I had to give the same lecture, and while doing so, I wrote careful notes, but I was a bit slower in this lecture. So now you have most of the previous lecture covered in the notes, and I will quickly repeat the other things that we said. So the ideas, well, I do believe that you remember what is Turing machine. So it has tapes and it can make one computation step. I mean, it steps and so on. And it can halt or not halt. And we had a special such machine because we considered machine with infinite input. And so there was a special tape where the infinite bit sequence for input was written. And also it has a special output tape, a printer tape. So it can send bits to the output, but the head can only move in one direction. Once a bit is written, it cannot be changed anymore. And so there's infinite input. And we are interested in probability. So we will place a random sequence on this machine. So it's just a probabilistic machine where we make the randomness, the random coins visible for theoretical analysis. So in Vereshchagin and Shen-Uspensky book, they will just not speak about Turing machines and just work with any machine from algorithm scores or something. But it's very nice if you do it like this way, but then everything has to be done very carefully. Okay, so so input is infinite, and then there is printer. Oh, let's write the printer here. Printer, and it produces output B1, B2, B3. So the machine can never halt and print an infinite sequence. So for example, you can have a machine that ignores the randomness and just prints 0, 0, 0, 0, 0, and so on. But you can have machines that simulate that make some complicated computation, then print a little bit, and then get stuck in a loop, and then unfortunately not print anything anymore. Okay, so this is the machine. So we can, and there exists a universal such machine. And so what do we mean by this? And so there is a machine U. So let's call U is monotone universal. If we can, if it can simulate any other machine, provided we put a special program. Okay, I will speak about later about this. Let's not speak about this. Let's just give our machine a name UV, and then we will define a probability BV of X is equal to probability that output starts with X. And so the printed bit is X plus something. So let me write it a little bit different. So let us make the P explicit. So probability V on input P is equal to X followed by something. So this is the idea. So why did Solomonoff think about this? So actually, this was 1956. He had this idea, and he was in. He followed the course on foundations of probability, and he went to some summer meeting with about 10 people for 10 weeks, and all the people who were there became famous scientists. So maybe Shannon, you heard about him. So Shannon information. There was McCarthy who invented important programming language. There was Minsky, who is very famous in artificial intelligence. And one of the ideas they discussed was, is it possible to build a machine and you give it observations from physics experiment and it infers polynomial rules for prediction. So for example, you drop a stone from several heights and you give the machine a list of height and the time, height and time, height and time. And then you give it a new height and you ask about the time. And so then machine should understand he takes square root, multiply, multiply by 2 over g comes. So there is h equals g over 2 t squared from physics book, right? So you need to integrate speed, and the speed goes up linearly. Okay, so yeah, and so then he says, okay, there's a sequence prediction model. So you have alphabet. So alphabet is equal to the numbers 0, 1, 2 till 9. So you also need the dot, and then you have you need to tell the time and the height. And so you can create a sequence of inputs. So for example, height 5 time 1, height 20 time 2, and then you say what is about height 10, for example, and then you say t, and then the algorithm should understand that here should come the correct answer. Okay, let's say something I know the answer. So if I double, so that will be, and then the idea is that machine thinks that the next bit will be 4 with high probability. So on some bits, it cannot say anything. For example, if you say H, it doesn't know what you will say because it doesn't know what experiment you're planning to do. But then when you ask T, it should understand that there is interpolation happening. So this example of how building a machine, and then he understood that he could build such a machine. And there was also Noam Chomsky, is also a famous guy, who gave a talk in a conference about finite state machines. And then he made a second paper where he applied to finite state machines. And then a bit later he said, oh, but Turing machines are even better. And they provide a kind of optimal system. Okay, this is about history. So let's okay, let me look what I'm supposed to say because I already forgot. Yes. So then the next step what we already explained. So the idea is to look at conditional probability from this measure PV. So to predict what is the next bit, we will look at PV of XB divided by PV of X. And so we will say that this is a conditional bit after seeing X. So it's visible in the camera. Let me. By the way, it's a bit dark here. That's all the lights are on. Okay. Yeah. So here we have conditional probability, and of course the idea is that with 4 the probability is large, for the other it's small. Okay. And we understood already. We gave an example. Like imagine that we we want to predict the next bit, so we just have to say 0 or 1, not a probability, and then we prove that if we optimize conditional probability or just the probability itself, so if we have a measure Q and each time we predict as next bit, so we see X and we get the next bit B, and we optimize this probability, then our predictor, so imagine that we have X1 till Xn. And so our prediction for the next bit, when we choose this predictor, then number of mistakes, you remember, was the binary logarithm of 1 over Q, right? And so this was the idea that the bigger we can make our measure, the better will be our predictions. And so we say that this predictor, it was from previous lecture, makes at most log 1 over Q of X mistakes. So here X is finite string, and then N goes from 1 to the length of X minus 1 for this prediction. And the reason is that each time we make a mistake, the measure goes divided by 2. Okay, and so the question then, Solomonoff thought, how can I find the biggest probability here? And the answer is we will take a universal measure here. So we take a kind of universal machine. So we want to find a measure that's maximal. But a maximal measure, we will see, doesn't exist, but we can have a maximal measure up to some constant. And this is what typically happens in algorithmic information theory. We can do something optimal up to arbitrary constant. So we can discuss about which maximal measure we will use. And so now our task is to understand that how can we choose a maximal measure? And our first attempt is when we look to our predictions, the first attempt might be to try a computable measure that is maximal. But a maximal computable measure does not exist. So let us make a first lemma here and prove that there exists no computable maximal measure. And so ID used by using induction with optimal measure. Okay, let us first say what I mean with a maximal measure. So we will say that a measure P is better than a measure Q. So we say P is better than Q. Or let's do the direction Q is better than P if there exists a constant C for all X. P of X is smaller than C times Q of X. And so basically P is big O of Q. It is slightly different because we have to, then we exclude finitely many variables. So we say that Q dominates P. So Q is better than P, but means that we will make, if we use Q instead of P, number of mistakes on each sequence or each string will be at most finitely more. And remember, so this log Q Q can only be, so if Q is better, it means that Q can only be lower, smaller by a constant factor. So our number of wrong predictions will be at most log over C more if we use Q. But it may be that on some inputs, Q is much bigger than P. And so on some inputs, we may have unbounded advantage. For some infinite sequence, it might be unbounded advantage at the cost of making finitely more mistakes on other inputs. So that's the plan. So, and now the question is, can we find a Q that is bigger than a constant compared to all the measures? If we don't use computability theory, it's impossible. So why is it impossible? Oh, yeah, I can ask you. Why is it impossible? So if we don't place any restriction on P and Q, so then there is no maximal measure. Sorry, I didn't say what I mean with measure. I said it previous lecture. So please, I forget to explain everything because I am in emergency state and so my brain just erased at each next task. Okay, so what do I mean with measure? So measure will be a mapping from strings to non-negative real numbers. And so there are two conditions. P of empty string is equal to 1, and for all strings, P of x is equal to P of x0 plus P of x1. So I explained it last time. You need to tell me. Okay, if you forgot. So, okay, and now I claim that there exists no measure that dominates every measure, every other measure. So why is it?
That's one for all the things that such as one, and the other measure that's one for all the things that such as zero.
Ah, okay. So you say, let's look at two measures and they don't dominate each other. But that's, sorry, you say, let's choose two measures and then say no one dominates both of them. So thank you very much. But it's not correct, but it is it's a very good example. So okay, let's remove it. So let's take, they call this deterministic measure. And so the proposal is measure 0n is equal to 1 for all 1. So that let's call it P0. And then P0 for any other string that's not of this form will be equal to 0. So that's what we say. So let's say omega is equal, sorry, Px is equal to 0 for x in 0, 1 star minus 0 star. Okay, and then we can do the same with x 0 and 1 flipped. And so we have P1 like this. But then we can look to P0 plus P1 divided by 2. So this is also a measure. I take linear combination, and here I have linear conditions. So it's also a measure, and we have that P0 dominates this measure. Right? So what is the constant C that we use to see that P0 dominates the mixture? And so we set C equal to 2. Right? So then we have, so So I claim that we have P0 is smaller than 2 times 1/2 P0 plus P1. Right, so this will be our C and the definition there. So, but proof has, or half of the work of the proof is done by this idea. So just 2 measures is not enough. We need a bit more, quite a bit more. But we can use this idea to construct a problem, if we believe that there is no. So somebody can do the second half of the proof. Okay, so here we have 2 simple sequences. All zeros, here all ones. And I said we need a bit more, quite a bit more of such measures to create a problem. Okay, yeah, actually there is a better way to prove this. So when I take any measure, I can find an infinite sequence. Oh, no, sorry, it's my first idea wrong. So when I take any measure, let's call it a measure R, I can find an infinite sequence so that after n bits, this measure is smaller than 2 to the minus n. Agreed? And so we can represent measures on a tree. Okay, what shall I remove? Let's remove this and write it later. So measure can be represented on tree. So here we have empty string, 0, 1, 0, 0, and so on. Let me write a bit more. Okay. And so let's now go down and at each step take the child for which the measure is smallest. And so we compare P0 and P1 and we take the smallest direction. For example, we go here, then maybe we go here and here. So that means in each child, the measure goes divided by 2 and so on. So if I give you a measure, you can tell me a sequence, an infinite sequence, omega. Sometimes the people such that P of x1, xn is omega 1 till omega n is smaller than 2 to the power minus n. So for all the n. Okay, and now let us go back. Imagine that you claim your measure is universal. That your measure dominates all other measures. Then I will look for your measure to this omega. And then I will compare it to the deterministic measure that concentrate everything, that has all ones along omega. So then the deterministic measure is exponentially larger than your measure. And so we find the contradiction. So there is no measure that's better than all other measures. Okay, now second attempt. And so for our induction machine, we don't have a maximal measure. But so basically what's the problem is that number of measures is uncomputably many. It's too much. However, if we only consider countably many, so the computable sequences, the computable measures, then we can create such a mixture actually and get a maximal measure. So for any computable, any countable selection of measures, we can create a measure that is bigger, that dominates all of them, just by taking the mixture here. So let me write it. So if S is a set of countably okay, let's have a sequence of measures. If P1, P2, and so on, this sequence measures. Then, so I need some weights to weight them. So then let us call it N. M of X equal to sum of I, Wi, Pi of X. Dominates all these measures. Then M dominates. So here we say P dominates. Sorry, Q dominates P. Then this measure dominates Pi for all I. And so why? Here we need coefficients. So I didn't say anything about coefficients, but here we require that sum of Wi is at most 1. Well, it needs to be exactly 1 if you want measures, and Wi must be bigger than 0. Then this will be true. So that should be in the beginning of the lemma. So yeah, it's a bit messy. I will write it nicely in the lecture note. Okay. So if we have coefficients satisfying this, then we get the measure that dominates all of them. And so what we could do is consider a list of computable measures, a list of all computable measures. So what is a computable measure? There exists a Turing machine that on input X outputs the value of the measure. So this is easy if we think about measures with rational values. Yeah, so this is easy. But there is a little problem. We cannot make a list of all the computable measures. And so if we, I mean, we can make a list, but we cannot compute the list of all computable measures. So you can, if you could do this, then you could do something like we did for the halving problem. So this measure will not be computable if we do this. I will prove it again in another way soon. Okay. So we could choose, so this is the message. So if we choose a really weird measure M, then we get something that's not computable, not lower semi-computable, nor upper computable, but it will be able to model all the computable measures. In the sense that we say, according to in the weaker sense that we say, when we predict according to the maximum extension, the maximum probability of extension, we will make finitely many mistakes whenever P is deterministic measure. So, okay. So what turns out to be the problem with this approach is that these equalities here are screwing with us. And so we think about measures, and then we end up in a theory where we cannot compute anything, not even approximate things. And so we will solve this problem by having, okay, here, this is not important, it's just one value. What counts is that here we have an inequality here. That will be our plan. And this is precisely what is achieved by Solomonoff induction with this random input of the program. Px, you mean? Yeah, so in the machine, so we will look at the probability. So this will be a probability that the machine, prints something starting with X. And this probability is bigger than printing one of the two extensions. It might happen that the machine gets stuck after printing X. So it starts to compute something but gets stuck. And that's why there is excess probability. And this is very important that we allow this. Otherwise, we get into contradiction. Okay. So now let's go back to, so the next thing that what we will do now is we will consider lower semi-computable measures, and I will prove that Solomonoff's measure will dominate every lower semi-computable semi-measure. And so if you have an inequality, it's called semi-measure. And do you remember from previous lecture what means lower semi-computable? And so we can enumerate the lower graph, or equivalently, we can, I didn't say give a third definition. We can have a function, a computable function. I have a little space. So f is a lower semi-computable if there is a computable function with two arguments that is increasing in the second. So if we can compute a sequence of approximations that increase and the limit reaches the value of the function. So f is lower semi-computable if exists computable phi such that two conditions. One is that phi is increasing in the second argument. And second condition, limit for t of phi of x equals f. Oh, and it's visible on the, okay, but why did I say this? Okay, so the claim is that Solomonoff's suggestion for prior distribution will dominate all lower semi-computable semi-measures and is a lower semi-computable semi-measure itself. So let me put it back, Solomonoff's machine. Well, it will be such a machine if we choose if we choose universal monotone machine. And so here we have our U, we have the printer that creates the output, and then we have infinite entropy. So there is some P and 0, 1, uniformly random. And then we say that we start with general machine P, and then we have PV of X equal to probability V of P equals X followed by N. Okay. So our first task, let us verify. We also did it last lecture. Let's repeat it quickly. This is indeed semi-measure, and we already explained this, right? Probability of empty string is 1, and it is lower semi-computable. So how can we get a function xt? We can evaluate on all the randomness t. So for all randomness for up to t steps, we evaluate the machine for t computation steps. So then it will check. So we check the machine for t computation steps, and we collect all the randomness that print x. So then we have to check 2 to the power t choices for the randomness. So it's very slow process, and we check it for t steps. And then we count how many of these random strings produce X. And in this way, we get a lower approximation phi. And when the limit goes to infinity, we will get the right probability. So it's lower semi-computable. So, and for any monotone machine, this is lowest semi-computable semi-measure. Now the other direction is also true. If I give you lower semi-computable semi-measure, we can find a machine that produces this probability. And so here is the lemma. If Q, or just say, Q is lower semi-computable semi-measures if and only if there exists monotone machine. I will abbreviate monotone Turing machine, MTM. There exists monotone Turing machine V such that PV equals Q. So this is the lemma, there is equivalence. Okay. So now our next goal is to prove this lemma. This lemma we will use to understand in another way that there exists a maximal lower semi-computable semi-measure according to this relation, domination relation. Okay. Okay, so now we have a semi-measure Q. We have to first let's define a way to generate monotone machines, to construct monotone machines. And so I claim that if I can enumerate a list of pairs input, so X is a string here, not the first bit of some X. So here Y1. So if and Y1 and Y2, they are intervals so let's consider the real numbers starting from 0, so unit interval of real numbers. And so I will, if I can generate a list of strings and intervals in 0, 1. So we will generate lists of pairs, and from this we derive a monotone machine. And the monotone machine will work as follows. It will interpret the random sequence as a number, then check whether it's in any of these intervals. And if it is so, it will send the string to the printer. So here we have a sequence of strings, 0, 1 star, times, and then intervals. So when I can enumerate such a sequence, I can construct such a machine. But there is a condition on this enumeration of sequences. The rule is that if two intervals intersect, then so if such that if ij intersects ik, so it is non-empty, then either xij is a prefix of xk or xk is a prefix of xj. Then xj is prefix of xk, or xk is prefix of xj. Okay, so I claim if I have a machine like this, so if I can enumerate intervals like this, so that this is satisfied, then I have defined the machine here. And so for the machine, there is only one obstacle to generate it. So So how the machine operates, it looks at, it enumerates the intervals, and each time it checks whether its random input is in the interval. And if so, it looks what it has already printed. And if x2 is longer than what was already printed, it continues to print. It prints the new part. But if it sees something that, but if it sees another string, then by this rule it must be a prefix, so it won't print anything. So if the string that it receives is shorter than what was already printed, it does nothing. If it's longer, it prints the difference. And this is correct machine. So we need to verify that it never needs to erase something that was already printed to keep to keep the invariant. That each time p belongs in the interval, x2 appears on the printer. That's the invariant of the construction. It's quite easy to explain. So to understand if all formulations are correct. So claim is that if I enumerate a sequence of string interval pairs that satisfy this condition, then I've constructed a machine that is a printer that prints according to the rules. So it's okay. Once I have this, I got a machine. Or for one person, it's okay, but I want, okay, if I guess from faces, 4 people are okay, but there is 7 here, so, but I can, you need to say something. Okay, then it's okay. Yes. So now we are given a measure Q, it's lower semi-computable. And I will generate such intervals, and then we are done. But so the plan is that for a given string x, and the disjoint union of all the intervals that have x, and so for a fixed string x, we will look to all the intervals that have this x appearing. We take their union and decide the measure of this union must be equal to the measure of Q on the string. So that's what we will do, and then we are done. And we just have to make sure that we can enumerate this sequence, and that the total measure of intervals for a fixed x is equal to the value of Q. Okay, how does it work? And then, of course, we have to check the prefix relation. But then the construction is the natural one. So how does it work? And so let's consider a string xb. So just a finite string x with 1 bit appended. And let us say that we already constructed some intervals for the string x as well. So the plan is that here on the line between 0 and 1, we will have intervals labeled by strings. And so in our construction so first of all, for the empty string, we will just fix the full interval. And now we will continue with the construction by induction on the length of the string. So imagine that at some time t, and also by induction on t. At some time t, we have already enumerated some intervals for x. So here is some interval, it's labeled by x. Let me use black for intervals from x. So x, but there can be several associated to x. We can assume that they are disjoint. That doesn't matter. We can, whenever we enumerate something, we can check it's disjoint from, and if it's not disjoint, we break it up. So, okay. And now, so let us look to our computable approximation. And so we have a certain value at a given time step, t, opposite order, xt. This is our approximation for the measure Q. What's our plan is that we just randomly assign intervals inside the x intervals. So this is also labeled by x. We will now, and here we have the value of xb. We will randomly assign intervals to xb here, to the bit xb here. Maybe on previous stages there were already such intervals already assigned. But we try to assign intervals as many as we can inside the x interval. Inside the xb interval, but not disjoint from intervals of x not b, of course. So we can have a measure x not b. And these measures, we try to stay disjoint from them. So we just look for all this, we just do greedy algorithm. When we see that there is an update that at some point phi xbt increases, we try to allocate all the space inside the interval of phi xt. So we assign intervals there. And we just follow the rules. We stay disjoint from x negated b. And we just apply. And when our space is used up, we don't do anything. So maybe we don't allocate all the space of phi xbt. But just we allocate all the space we can to these intervals until all the space of phi xt is already allocated. And that's it. And so we do this for all the t, and then we increase the t, and we again start from the empty string. Well, we don't have to do anything there. And then we go to phi for the string 0. We see whether phi increased, and if it increased, then we allocate new intervals, and then the same for 1, and so on. So it's just a natural algorithm. You have to allocate things. So you have the 0, 1 interval. You allocate intervals to all the strings. So let's do. So for every t, let's look. Okay, let's do it a little bit from. Let's go over the algorithm from scratch. So what happens at the first time step? And so we have some value. So what happens at time equal to t? So for empty string, we don't do anything. So let's look to the string 0. So this is the bit 0. And let's look at the first time step. So then we have the unit interval. And then we calculate this value. So it's rational. Well, I forgot to say. Here I have a slower semi-computable. Here phi should be rational function. So it will be, let's say, from strings to q. Okay, it's just visible. So here we have a rational value, and then we assign an interval here. So of length, so we label it by 0, and the length is phi 0, 1. And then we do the same for phi, the string 1, also the time 1. That might be something like this. So we just take a place, and we assign this to the string 1. And then we go to t equal 2. So we assign new intervals here. And so here we have assigned the first 2 intervals in our sequence. Then in step 2, we start again. For the empty string, we don't do anything. So then we will look at phi 0, 2. Phi 0, 2 might be a bit bigger than phi 0, 1. And so we allocate. And so in the second step, we allocate a new interval to 0 again. Just we look for free plates, an interval that's not assigned to strings of length that of 1. And then we allocate this interval again to the bit 0. And maybe phi 0, phi 1, 2 remain the same. And then we go to the next string, phi 0, 0, 2. And phi 0, 0, we assign inside the two intervals. For example, the same interval might be labeled by 0, 0. And so then we enumerate the third one will be this thing. And so maybe we need a bit more. Okay. And then we go to phi of 0, 1, 2. And this might be non-zero, so we allocate a little bit here to 0, 1. And then we inside in the first, so we look to phi 1, 0, 2. If it's positive, we need to allocate something. And so we repeat. It may happen that, for example, phi, the sum of phi, these two, phi 0, 0 and phi 0, 1 is bigger than phi 0, 2. Because we are only guaranteed that the phi's increase. So for the approximation, we don't have a guarantee that this holds for approximation. But that's not a problem. So we just allocate. That means that for phi 0, 1, we need to allocate more than we have intervals labeled by 0. But then it's not a problem. We just allocate everything we have and we continue the process. So that's the algorithm. And why it's not a problem? Because we know in the limit, phi 0, 1 will be increased. In the limit, this will be satisfied. So later in the future, we will increase intervals. We will have more intervals labeled by 0, and then we can allocate them. Okay. And so now we understand that while doing this process, we approximate the measure Q. And for every string X, the union of all the intervals allocated to X will be the value of Q. Because we follow the value of phi. So it's the natural process. And so now we understand that we can build Lauer semi-computable semi-measure. Okay. So for homework, there is a similar question. So there the measure is computable. And then you have to prove that the obtained machine is defined with probability 1. But it's also quite logical. Okay, and I will write this carefully in the notes. So then it should be easy to read. No, but if you want me to explain again, there is no hurry. Yes.
Again, why is there other two intervals of 0 things assigned to 0?
Yeah. So in the first step, in the first approximation, we only had a little lower bound, a small lower bound for the value Q0. But then in the second step, we discovered that we improved our lower bound phi. So we discovered that Q0 is actually larger, but we didn't know it at the first step.
So we increase our interval.
Well, we generate a second interval, but also assign it to 0. And so we will have infinitely many, we can have infinitely many intervals assigned to 0.
So as the measure increases, we get covering the full interval.
Yeah, we cover more and more.
And thus
Yeah, well, we know that,
finite where your Q.
yeah, Q is measured. So we know that it's always bounded by one because of these inequalities.
And why does the measure increases 100?
Well, we assume here Q is lower semi-computable and definition is there. And so we have here a lower approximation that increases. Yeah, yeah, exactly. Okay, and now we have proven our very important theorem. So the corollary of this lemma is that there exists a lower semi-computable measure that is multiplicatively optimal, dominates all other lower semi-computable semi-measures. And it follows from existence of universal machine. That's a machine that if we prepend certain prefix, it can simulate other machine on the randomness that comes after it. So maybe I should rewrite this theorem, this other result of universal machine for monotone. So we have a theorem. I don't know, maybe I should call it lemma as well. So there exists a monotone Turing machine U, such that for every monotone Turing machine V, there exists Q for every P. So here Q is a string, let me say it nicely. When we prepend randomness for V, when we take Q and append randomness for V, U is doing what V is doing. So that's the idea. And so there are many quantifiers. So for all there exists Q, which is finite. Then for all P, which is infinite. And so we have that U of QP is equal to V of P. So it is universal monotone machine. So let me say it again. So I say that we can have a single machine. For any other machine, we can simulate other machine on input V by prepending compiler, V2U compiler. So this is a little bit like you have Python and C++, and then you want C++ code that execute a given Python program. And so you combine the two programs, and then you have interpreter for Python code that uses C++. Okay, then you need C++ interpret. Okay, compiler. Let's say it's like this. So, so you combine compiler for Python. I think it exists. No, I don't know if it exists. Yeah, they're bytecodes. It is special files. Okay, so we take Python compiler and C++ compiler, combine it together, and we get new Python compiler. Yeah. So we get Python compiler from C++ compiler by. Okay. So what does it mean? For this universal compiler, the result is that P of U is, sorry, P of V is smaller, multiplicatively smaller than P of U. Because this we discussed last lecture. Here we said that P of V of X is smaller than, so when we take the Q for V, let's call it QV, is smaller than 2 to the power So sorry, let's multiply it like this, times 2 to the power minus length of QV times PU of X. So why is it true? So probability that V guesses an input producing X. So probability that V starts to produce X is at most probability that U guesses this specific Q and some program that makes V produce X. So this is corollary, so we have PV is bounded, PU dominates PV here. And now from our lemma, we know that for every lower semi-computable measure, we have such a V that produces lower semi-computable measure. So for every Q, we have a measure VQ that dominates U. So we can say that Q is equal to VQ from our construction in the lemma, and this is bounded by PU. So we have proven that if we take such universal machine in this probability, the corresponding measure is bigger than any other lower semi-computable measure. So we did already 1/2 of the work. And by the way, so if we have a program that computes Q, we can understand what is this constant QV. It will be a program that simulates this, that computes this measure Q. And so if we have a small program that computes Q, then this constant in this definition, this constant will also be small. It's basically a program, but it needs to be a special program because right after presenting the program starts the random bits. So we need to also write in the program, I will be finished, my code finishes at this position. So in the beginning of the code, we need to write something or somehow implicit in the code, it should be self-delimited. Okay, but this is technical result. So what I am saying is that the length of this code tells you something about this coefficient. And we know that this coefficient is also important in our bounds on the number of mistakes. If this coefficient is very large, then we might have more mistakes. A constant number, but maybe a large constant number. Okay, so let us now go to finally to Solomonoff theorem. So we will fix universal measure here. And then Solomonoff says, I can optimally approximate any computable measure. So unfortunately, in the proof, something goes wrong for semi-computable measures. So he will be optimal okay, we don't need any low-level details anymore. So what we will use is that, yeah, so I didn't write what we will use. So let's write it here, just the definition. Let M be a lower semi-computable semi-measure such that for every lower semi-computable. So this is called, so the machine we obtained, the measure we obtained here is called multiplicatively optimal lower semi-computable semi-measure. It's a very long name, so, but nobody, so, yeah, let M be lower semi-computable measure. That's multiplicatively optimal. So for any lower semi-computable measure Q, we have that Q sorry, M dominates Q. And so here we are implicitly using that such an M exists, and we just proved it. Okay, and now I can finally say what is Solomonoff theorem. So if P is computable, measure, then expected value for omega taken from P. So we generate infinite sequence from P. And then we will look to the conditional measure, next bit given previous bit, and then the squared error. So the sum of the squared error of conditional probabilities will converge. So sum over n, sum over y given x1 till xn minus n y given x1 till xn squared smaller than maximum, let's say supremum of m z logarithm, the natural logarithm. Supremum, and here z goes over all strings. So this is our main result. So
What is the output of M y vanishing x?
So what is this here? Yeah, so this is conditional probability. So it is x1 till xn and y divided by m x1 till xn. Oh, sorry, no, okay, I use x for infinite sequence now. Okay. So this is a powerful property. So when we generate x from a computable measure, then a priori probability, the conditional variant, will converge to the correct conditional measure. And so in a very strong sense, so we take the sum over all the errors, and it will be bounded by a constant. And actually, there is a measure concentration result. So if you take the bound a little bit larger, it will be with exponential probability, it will be near this lower than this upper bound. So there is like Chernow bound is valid for this expected value. Well, to be precise, we need square root in this formula. I forgot for squared error what is the result, but okay. So it's not only expected value is good, but also there is pretty good bounds.
What
Yeah.
does that represent?
What?
That?
Yeah, supremum of the natural logarithm of a ratio.
That is a value that.
Yeah. So and well, let me say something better. So it's a bit on the so let me write it. I think it's just me not writing carefully. So it is bounded by supremum, and so we look over all strings 0, 1 star, And then we look to the ratio, sorry, to the natural logarithm of the ratio M of Z. So here we have unconditional probability. And we know something more, that this is bounded by a program length to compute P. So this is bounded by ln2 times, so we don't have binary logarithm, so that there is power 2 to the q here. Bounded times length of program that computes of approximate P. So and so here there's we have plus of 1. But it has to be a self-delimiting program, and then if you give it the string x and some time t, it starts. Okay, so this is a bit informal here, but it's the idea. So the idea is that if you can compute P with a very small program, then it will converge very fast. So let us consider the program that prints all zeros. So let us have measure concentrated on all the zeros. What is it saying? It will say that squared probability for predicting 1 will converge. And so we can set y equal to 1. And in the correct model, this will be always 0. So the square of the probability to predict 1, it will converge, the sum of it will converge to 0. That's what we're saying. But there is also the result. So this result, it has some technical things. We will prove now something slightly different. We will look at square root here. So it will be a bit easier. And then in the example, it's even better. So sum of probabilities to predict 1 will be bounded. So precisely the same result holds with square roots on the probability. Okay. So, okay, let me write it. So imagine that P of 0n is equal to 1. So you know that all other strings have probability 0. And so what do we get in the formula? So expectation, we don't care about it, and because we will only sum over 0n. And here in the sum, I will take something smaller. I will only set y equal to 1. So what do we get then? Is that sum over n? That's the only. So I delete the sum over y and the expectation, because for every n, everything is concentrated in all the zeros. X's are all zeros. So then we have P of that. Yeah, what is here? Py1 given all zeros is equal to 0, right? So what we have here is 0 minus square root of m1 given all zeros. And then we take the square. And the claim is that this is smaller than length of program that only prints zeros. But this is just a small constant on the universal machine. So it's smaller than O of 1. So if we believe in Solomonoff prediction and we see 0, 0, 0, 0, then so actually you can think, so there is a story in Hutter book, so he really cares about this problem. And he says that every day you wake up and the sun shines and you're scared you will wake up, sun doesn't shine anymore and everyone freezes to death in just a few days. So what is probability of this happening if you don't know anything? So you only see sun going up and down. And then he wants this probability to be small because otherwise he's scared that suddenly everything will change. And then he says, oh, if I believe in Solomonoff prediction, then at least it's bounded. But for Bayesian induction with typical priors, it will diverge. It will be infinite. And also there is something interesting. In the seminar, we were thinking about this measure. We said that when the number of zeros equals busy beaver function, it jumps up again. If there, so at moments where we have a length of zeros that's computable by a very small program, suddenly our measure becomes big again. And that means that we are in a special time. A special, so in the story with the sun, so we can think about beginning of solar system. And then at some point, there is a special time defined by the way we describe solar system. That is somehow simple. It's a time where something might change. And so I think that this kind of justification, so there were people who think that Mayas were very clever physicists, and then there was a year 2012, I think, that I forgot the year, but I was alive, and everyone was really scared about 1st of January because the Maya calendar was finished. And so if you believe that these old people were very clever and understood a lot about physics and they had ideas about the stars and so on, so these people believed something would happen. And so it is because according to this logic, this number is very special and hence has a very small description. So you can think about the measure where at this simple moment something changes. This measure also is easy to describe, and this measure will be dominant around this time in the mixture. Therefore, people become scared. So there are many things to say, but of course it's hard to believe that the Mayas knew much more than current scientists. So I was not worried on this 1st of January. Well, I can be worried because other people are worried and do something stupid, but it's other argument. Okay. Yes, sorry. And now we have to prove the theorem. And so there are 2 steps in proving the theorem. So this we more or less understand already. So the only thing we don't need to prove is this inequality. And it goes in 2 steps. So this is basically Hellinger distance between conditional distribution. We replace it by entropy bound. And nowadays, people in machine learning, they use it a lot, entropy bound. So I guess you also know this. The divergence, Kullback-Leibler divergence. So it's upper bound on Hellinger distance. And once we have Kullback-Leibler divergence, this bound becomes really easy. So these are the 2 steps. Okay, and then it's basically time. But so what shall we do? So we have a break now, and then I explain for 10 minutes, finish the proof, and then start with seminar, or do 10 minutes more and then have a break. What do you think? Okay, then let's do 10 minutes more and we will have a rest afterwards. Then maybe cafeteria is empty or something, so it can be good too. Okay, first step is we have this ugly square roots, we will get rid of them. And so given two measures, so we have two vectors P and Q, and then so Hellinger distance P and Q is equal to square root Pi minus square root Qi squared. But then we also have Kullback-Leibler distance between the vectors. So it will be Pi ln EIQI. So this you will need to learn for other courses anyway, so you can start to remember it already now. So Kullback-Leibler divergence, none of them is a distance measure, and this is really ugly because it's not symmetric. And none of them satisfy triangle inequality. Square distance also doesn't satisfy triangle inequality. Okay, and the first lemma is that Hellinger distance is bounded by Kullback-Leibler distance. So, and it's kind of computation. I will skip it and you will need to learn yourself, but it's easy. It just basically it follows from the bound ln x smaller than x minus 1. So you plug in this bound here to get rid of the logarithm, but you need to apply it to the square root of the logarithm. So you will do this, apply this bound, and then everything cancels. So it's really cool. Okay, now I remove the logarithm. So this lemma is proven. And so what remains here is we have to prove this, but now with P. So here we will use, okay, I will delete it and write what we need to prove now. So we will use the bigger one. And so we will have sum of Py given, let me abbreviate. So let us say x at most n is equal to x1 till xn. And so we have here ln P y x bounded by n divided by q y x bounded by n. No, and there is no square anymore. So we need to prove that this small. Okay. And now you see something cool, right? There is a sum over y and there is probability in the front. So what can I do? I can get rid of the sum, but I need to change a little thing here. I need to replace y by xn plus 1. So let me rescale a little bit and so then it becomes easier. So it's less writing for me. So you see that I can replace y by xn and drop the probability. So why? So look, here is definition of expectation, where y is a random variable distributed according to conditional measure here. But what here we have expectation, x is infinite sequence. So what x first n minus 1 bits are distributed according to p, and given these bits, the n bit is distributed according to distribution. So xn and y, they are equal in distribution. And so, okay, let me write it in full. I remove this and write expectation over y according to conditional measure. Okay, so I draw y from conditional measure. But then y has the same distribution as the n bit here. they're equal in distribution. So I just replace y by the n bit. I take another variable with the same distribution. So I can do something cool. I write here xn. Okay, it looks like I'm missing something formally. I will think very long because you look confused at this point. I will think very long and carefully if I'm missing some technical detail. But if they're equal in distribution, you can just, what am I using here? I replace one variable with the same by another one with the same expectation. And so in each term, I can do it separately. I don't see any trouble here. Okay. So now let me write what we have in the left-hand side. So we have expectation x from p. And here we have a sum over n. So we get rid of the y. Sum over n, ln p xn given x smaller than n divided by q xn given smaller than n. And now it's easy because the logarithm we write as a sum. And then if we work out the sum, we have not a supremum here, but expectation. So that I messed it up. So I mean, I made it ugly. So what was here? Supremum of ln of ratio. But we will get, instead of supremum, we'll get expectation ln of ratio. Okay, I write the steps. So we have expectation over sum of n, ln p of xn given x smaller than n minus ln q of xn given smaller than n. Now we look to the sum. Sum, so we flip sum and ln become ln of product. Product of conditionals become full distribution. So we have here equal, okay, let us, here we have sum over finitely many n. So let us say n equal 1 till this, and then take limit for n to infinity. So it's still equal. The problem is that I want to work on something finite. Okay, now we have sum of logarithmic conditional probabilities. So we flip sum and ln, we get the product of conditional probabilities will be the joint probability. So we have limit n to infinity expectation over ln p x1 till xn minus ln q x1 till xn here. Okay. But then we have the ratio back here, ln of ratio. So then we take limit n to infinity. So here we have ln of ratio. Here we also have ln of ratio. So when we take supremum, we get an upper bound on ln of any ratio. And so the proof is finished. So that's it. That's life work of Solomonoff. So it's pretty cool result. And in seminar and homework, we will think about consequence. But first, we have break. Okay. Yeah, and you can ask more questions. I see some doubt in the eyes. There is something you want to ask, some of you, but